Okay, sorry, Rahul, you were saying you tried it?
Yeah, I haven't exactly like properly tried it, but after having a quick look at all of them, I can only, I think 3 or 4টা পারবো নিজে থেকে পুরাটাই, but the rest একটু দেখা দেয়া লাগবে, there's some
What
do's
about
and
number
don'ts and
one?
stuff.
Have you
Uh,
has
yeah, no, number
anyone?
one, I'll need help. I'll need help.
Sorry, I couldn't hear you. Okay, anyone else who has any idea how to do number one? Moon, did you figure it out? Sorry, Moon, your microphone is muted. Maybe you didn't hear.
No, sir.
Okay. Okay, so like think of it very physically. Okay. So let's discuss number one. So what do we know about this problem? Have we seen this problem somewhere else first? Have you
I
seen
think it's my
where
first time seeing this sort of question. So
where have you seen carbon monoxide before?
yeah, I've seen those stuff, but not exactly this sort of question.
No. In this course, where have you seen carbon monoxide being treated? The rotational degrees of freedom of carbon monoxide being treated in this course before?
A tutorial question.
Exactly. So you have to use the result of your tutorial question in this problem.
Yeah, I was going to the tutorial questions and read the book where
Okay, so
Binny
let's
and
start with
Skinner.
that. So remind me what the energy level of a diatomic molecule was in the approximation that we were doing in the tutorial. Does anyone remember?
Let's see. Energy. Which one?
What are the energy levels of a diatomic molecule, right? That's what I'm trying to.
Energy levels. I think it's J plus 1 times h bar square by 2
So
I.
E is a function of what? It's a function of J, right?
Yeah, function of J.
And that's equal to what?
J times J plus 1.
J times J plus 1.
And h bar square by 2I.
H bar squared by 2?
I. Yeah.
I, right. So first, so what information are we given? We are given that this is the energy level of a diatomic molecule, right? Right? This is the rotational energy level. Right?
Mm-hmm.
So what we are given is the frequency of the light that is emitted when the transition is from level 4 to level 3. L, this is L or J. And there's transition. And also when the frequency is given when the transition is from 36 to 35. So this is pretty low, right? So the first question is that, so this, okay, let's write this. So nu L going from, say, 4 to 3, and let's call this, say, nu 1, and that's given to be 461.04077 gigahertz, right? So what is the unit of frequency? What is the dimension of gigahertz?
Inverse second, I think.
Right. 1/time. Okay, and nu2, which is defined to be the transition between L equals to 36 to L equals to 35, that is given by 4116.6055, right? So now let's look at this energy level, the formula. So if I look at AE of J, E of J is going to be, h squared by, say, 2I, J plus 1, right? Now, if I look at, say, adjacent, if there is a jump from J to J minus 1, then it'll be EJ minus EJ minus 1, right?
Mm-hmm.
And then what we will have is that'll be proportional to h squared by 2I, and then we'll have J plus 1 minus J minus 1 times J, right? So if I work this out, what is it? It's h squared by 2I, J squared plus J minus J squared plus J, right? Then we see that this J squared, they cancel out. And what we have left over is J h squared by I. So this is for adjacent. So see that, the change in energy level, and therefore the frequency. So this would be the frequency, right? And that's equal to h nu. Sorry, not h bar nu, h nu, right? H nu is equal to this. Okay, so if I give you nu, you can go to this wonderful thing called the internet and find the value of h. All right, or you could, and then you could figure out what this value is, and then you could, I've given you what j is, right? For adjacent, this is j minus 1. If it's not adjacent, as in the first case, it'll be something a little bit more complicated, but you know what this factor is going to be. And you know what h squared is. So from there, you can find out what I is, right? Is that clear?
Yes, sir.
So the problem here is to, if I give you I, how do you find out what is asked in the question? So what is it they are asking in the question? Question number 1 is, show that these data in a non-rotating carbon monoxide molecule, the nuclear distance is 0.113 nanometers. Okay, and the electrons provide a spring, between the nuclei that has force constant of 1904 nanometers, right? So when they say non-rotating, what does that mean? That means that the rotation level is very, very small, right? So if I take, say, if I take a carbon monoxide molecule, so this is the carbon and this is the oxygen, I have to find out what this is, right? Yes. But if I knew what I was, the moment of inertia, around, say, it's around an axis of rotation that goes through its center of mass, then I could say, okay, its moment of inertia is given by, say for very, very small rotation, okay? So for a very small rotation, I can approximate it to be a non-rotating molecule. And the moment of inertia would be, what is the moment of inertia? How is it defined? M? Can someone tell me?
Mi and r square. Yeah, I r square. Ri, sorry.
Mi squared, right?
Yeah.
Is that correct? Right. So that's a moment of inertia around some axis of rotation, right? And of course, here the axis of rotation should be should go through the center of mass, right? Because if I look at the motion, the total motion of the total motion of an extended object okay, then what does it mean? It means that it's equal to the motion of the center of mass, which will be a rectilinear motion, plus a rotation around its center of mass, right? Do you agree? We know this from classical mechanics, right? So if I, okay, now you're saying how do I think of these things, right? Well, what is MO, the mass of the oxygen? So we are looking at a carbon monoxide molecule, right? So CO, and I gave you the atomic weight of those things, atomic numbers, right? So what is the, mass of the oxygen? Can someone tell me? I mean, not
16
times
some constant.
What is the constant's name?
The mass of the protons.
Right.
Or yeah.
And what is MC?
Twelve
Carbon.
times the proton mass. Yeah.
Right. Okay, good. Now, what do I know about, say, suppose the distance between them is S, then what do I know about, say, the distance from, the carbon, say, to the center of mass? What is that? Is the center of mass going to be closer to the carbon or to the oxygen?
Oxygen.
Right. So you know that the lighter the object is, the farther it'll be away from the center of mass, right?
Mm-hmm.
Right. So the idea is so if the distance between them is S, then the distance from the carbon to the center of mass would be the total mass, M. So M is MO plus MC, okay? We're ignoring the electron mass. Then it'll be M by MC times S, right? Do you agree?
Yes.
And then R of O would be M over MO of S. Do you agree? Okay, now we have an expression for I. I will be MO RO squared plus MC RC squared, right? So now MO is going to be MO RO squared is m squared by mo squared s squared plus mc m squared by mc squared s squared, right? So this cancels this. This cancels one factor of this. And so we have m squared s squared divided by m0 plus mc, which is what? M. So we get m s squared.
So wouldn't it be 1 over m0 plus 1 over mc?
Oh yeah, you're right. Yeah, sorry. Yeah. So this is going to be m squared s squared times 1 over m0 plus 1 over mc, right? Yeah. So therefore, the denominator would be m0 mc, and the numerator is m cubed, right? S squared. Is that correct? Did I make a mistake? Right.
I think it's
Sorry, do you think it's correct?
yes, sir.
Yeah, okay. Well, you're going to do your own mathematics, right? So you're not going to take my word for it. Therefore, S is going to be m0 mc divided by m cubed square root I of square root. So here, you know this, you know this, you know this, you know this. So you know this. Okay?
Sir, I had a few questions regarding this. Like, they have given like 2 different frequencies, one from shifting from 4 to 3, another from 36 to 35.
Right.
So don't we just need one here?
Yeah.
And I
you just need the one for 4 to 3 because that's
others don't match with experiment closely, as I read in the book.
well, this is going to be the one that is going to be, that's going to approximate a non-rotating, molecule, right?
Yeah. Okay, sir. I was just having different values. Like everything I got similar to what you did. Like when I just plug in the numbers, it just doesn't match. So
For 4 to 3?
yeah, and the difference is huge. So maybe there's something wrong I was doing.
Okay, I haven't actually done the sum, so yeah, I don't see how from the given data, one can find a different way of deriving this, right? So how do we find its spring constant, right? Did you figure that out, Mahi, or?
So I thought I still haven't wrote it, but it's like trying to like equate the energy with the the spring potential energy, like half of
Yeah,
A
exactly.
S squared. Like
But
the only
energy
problem
is
I'm facing in this
half
problem is just the numerical values aren't matching.
K S squared, right?
Yes, sir.
But the point is that we cannot take this value. Right?
Okay.
Why can we not take this value? Because this is the value for when things are not rotating. Okay, so what we need to do is that this is actually not S squared, this is going to be delta S squared, right? So it should be, delta S should be, when the spring is stretched minus when the spring is, in equilibrium, right? So we can take this to be kind of the equilibrium value, and we can take this to be the value, when the spring is when the molecule is rotating. And for that, we basically say that, okay, what if it's rotating and it jumps from L going to 36 to 35? So at that point, we know what the frequency is that's given. It's 4,115.6055 gigahertz. Okay. So from there, what we can do is that we can find out what I prime is. So let's call this prime, we can find out what because if, think physically, if this is spinning and we think of this as a spring, then, the distance between this would be longer than the distance if there was very little angular momentum, right? Do you agree?
Yes, sir.
So that means that, we are, of course, non-relativistic. So these, the masses of these guys don't change. So in our, expression for this thing, what will happen is mass will remain the same, but R squared will increase for both of them, right? So I prime will increase significantly, right? How do you find I prime? We find it from this thing, as we did before. And, and given that we know what I prime is, we can find out what S, the stretched S is. And because we now know both of these S's, we can find out what delta of S is. And then we can take the difference in the energy between, say, at L equals to 36 and L equals to, say, 4, and set that to E. And then using delta S, we can find out K. At least that's the idea. So, why don't you guys try out this idea and figure out the numerics? If the numbers don't match, let me know, okay?
Okay, sir.
Okay, so once you have found out what K is, you want to use E equals to H bar omega, where omega is related to, what is omega? Omega is square root of K, right? How is omega related to K? Force constant, Newton meter K. So it's half kx squared is equals to half m omega squared x squared, right? And m here is mo plus mc. So so k is going to be, so omega is going to be k by m square root, right? Yeah, sorry, I always forget this formula. So once you've found, and this is 2 pi nu, right? Is it? Yeah. And once you've found k, you can then, work out what nu is, and that should give you the vibrational frequency. So, okay. I think it's as simple as that. So there's a hint, and see if the hint, if the hint, matches, right? It should. We can check it now. Yeah. So what is M? MO is, we figured it out here. MO is 16. okay, so this is, so the numerator here, the denominator MOMC is 16 times 12 MP squared, and the numerator is 16 plus 12 cubed MP cubed. So what is 16 plus 12? It's 38, right? No, 28, right? 28 cubed, right? So we have 28 cubed divided by, what is this? 12 12s is 144 and plus 48, right? Is 192. Am I correct?
Yes, sir.
I'm terrible at these sort of calculations. So, okay, does anyone have a calculator that can calculate this? Okay, we can just simplify this because it should be 48 by 7, right? So if I divide this by 7, how much is this? 14.
Sorry, it's
Okay, it's the other way around.
343
Sorry?
by 3.
Shujash, what was that?
334 by 3.
334 is the numerator?
Yeah, the whole thing.
334.
34 by 3. No, 343. 343. 343, sorry.
Okay, so this is okay. So the numerator is 343 by 3.
Yeah.
That doesn't actually so did we make a mistake in this calculation?
Sir, I've been meaning to ask a question. What's the word for it? RC and RO. A little bit, Bob.
Okay.
Yeah, is this M by MC or like MC by M? Because then RC becomes greater than S if this is the term we're going for. Like M is MO plus MC. So overall RC is greater than S.
Oxygen is heavier than carbon, right? So R0 should be smaller than RC, right?
I mean, shouldn't like RC be, or RC or RO, like either one of them, shouldn't be less than S? Or
oh, I see what you mean. Yeah. Okay. You're saying that this ratio is greater than 1, and therefore, yeah, I think you got a point there. Yeah. So, okay, did I make a mistake here?
I feel like the ratio should be the other way around, but not sure.
Okay, let me see. What is the, yeah, just hang on 1 second. Okay, I just, let me look at the, okay, just one second. Let me look at that, look that up. Right, it's the other way around, I think, yeah. Yeah, sorry. Yeah, I think it's the other way around. So, yeah, you are right. So, so the idea is something like this, right? We have, say, this is, say, R1. This is, say, particle 1. Let's call it RO, okay? And this is, say, RC, okay? And then, we have some, then the center of mass, so is something like this. Oh, yeah. Okay. No, hang on. Let me just sorry, I've forgotten vector calculus. So let me just take if my reference frame actually, is something like this, and this is my, so what if it coincides with the center of mass, right? And so this is, say, R, O, and this is the oxygen, and this is, say, R, RC, and this is carbon, right? So and this distance is S. So S is RC plus RO, right? And then RC would be a fraction of the total thing, but since the carbon has smaller mass, yeah, you're right. So sorry, yeah, carbon has, so that distance should be smaller, right? No, that should be bigger, right? So the carbon should have RC in the denominator, right? Because MC in the denominator. MC in the denominator, and hang on, what am I doing wrong? Right. Okay. Okay, let's see. I think the best thing to do would be actually to take the rotation axis to going through one of the objects, okay? And then, okay, so this is kind of so the center of mass is this vector, and this is, say, R, and R is equal to M1 R1 plus M2 R2 divided by M1 plus M2, right? So in this case, this is 2, this is 1, and this is R2. So this vector. So in this case, R1 is 0, right? I'm just choosing it in such a way that R1 is 0. So I get M2 R2 divided by M1 plus M2. Okay, so that's the distance of the first object from the center of mass, right? You agree? So
Yes,
yeah,
sir.
it has to be the yeah. Okay, so if I call the first, so I can call it, say, R1. So the first one R, 1 is going to be. You're right. It's the other mass. Yeah. Okay. Thank you very much. Yeah, I think that solves it, right? Yeah. So that solves it. So if I go back, yes. So you were right, Shujosh. There was a problem with that formula, and the idea is, where is that formula? Not here. Not here. Yeah. Down below. Here. Over here, right? Yeah. So all of this is trash.
Yeah, I should have said this a bit earlier.
No, it's
Time
okay.
would have
Good.
been.
And you said it at the perfect time. I was doing something stupid, and you pointed out when you felt comfortable, and that's fine. Okay, so this is going to be M0, and then what did we find? This is going to be M, the total M, and this will be MC, right? Times S whole squared, right? Do you agree?
Mhm.
Isn't that what we found? Josh?
Yeah.
Yeah. Okay, good. So now, okay, that's very good. So then we get M squared, and then okay. So Nahid, is this what you did?
For the moment of inertia,
Yeah. Is this the calculation you did?
or um yeah, I mean, like, I just took from the center of mass and
So so okay. What I'm saying is that did you use this formula, this I, and this calculation to figure out what S was?
oh no, actually, I was trying using parallel access theorem,
Okay, I'm sorry. You were doing a sophisticated thing. Okay. Yeah. All right. So yeah. So now, okay, let's just see if our calculation is right, because it should agree with the hint. Okay. So so now I is going to be S squared by M squared, and then we will have M0 MC squared, right? And then MC M0 squared. And S squared. And from here, what is M squared? M is 16 plus 12. 16 plus 12 is 28, right? No, not 28. 38, right? No, 28. Sorry.
28, 28, yeah.
Yeah. So this will be 28 squared MP squared, right? And here we are going to get from the oxygen, we are going to get 16, right? Yeah. So 16 times এখানে carbon is 12 squared, And here I'm going to get 12 squared times 16. And here I'm going to get mp cubed, right?
Sir, 12 times 16 squared now?
Sorry?
The second term of like MCMO square. Shouldn't it be like
Oh, yeah, sorry,
12
sorry.
times?
It should be the other round. Yeah, sorry. Yeah. So this should be this, right? And then we have this thing goes away and this comes, right? And now we have to figure out this is going to be s squared mp. Okay, that's of course is good. And then we have 28 times 28. And so what is this? This is 4 to the power. Sorry, this is 4 squared, 4 cubed, right? 4 cubed times 3. And this is 4 to the power 5 times 3. 3 squared? Oh no, this is not cubed. This is what? It's 4, right? Am I doing it right or no? No, I'm not. Okay, sorry. I shouldn't be so clever. I just let me. Shujash, can you just calculate what the numerator is?
Yes, sir.
someone
It's 48 by 7. The whole thing.
Okay,
I
so
can calculate the numerator.
so that agrees with what the hint is, right? So we are on the right track. So I think you guys can pick it up from here, I think. Okay.
Yeah.
All right. Okay, that was problem number 1. So it took us 44 minutes to get problem number 1. All right. So
Sir,
let's do.
I mean, like in this problem, like I mean, this gave me no difficulty, but when I plugged in the values, like I just got something completely different. from
Okay, why
that.
didn't you plug in the values? Why don't other people also plug in the values, and then you guys can
acha.
compare your
Okay.
values? And so otherwise it'll just not be a homework session. It'll be just like a giving you a solution session, right?
Mhm.
So yeah, I mean, as I always said, do collaborate with each other on your assignment. Just don't copy each other, okay? All right, so what about question number 2? We did something like this in class, right?
Yeah. I
So it's
think
just
I
a
got
generalization of that.
yeah. Problem 2.1, I think I got that, but number 2, the explanation is a bit tricky for me. I'm not sure how to do that, so I'll probably figure it out later. But
Yeah, I mean that's a physical argument, right? So
Yeah,
yeah. It's about polarizations and stuff like that, So
Mhm.
Okay, anyone else wants to discuss problem 2? We did something like that in class, except in class, our direction was the direction of propagation of the particle was in the x direction. So, and the particles, we were assuming that our magnet or the unit vector was in the YZ. Sorry, the spin was oriented in the YZ direction. Sorry, yeah, that's what I meant. So there was only one angle, right? Only the theta angle. Now you just have to figure out how the phi angle also comes about. Okay, so it's a little bit of geometry. It's actually not geometry. It's just like you just have to diagonalize the matrix, a little bit of a more complicated matrix. It's still a 2x2 matrix. Okay, so since I've done it in class, you can just go and look at that. Okay, problem 3. Consider a quantum mechanical system that consists of 2 particles, one of spin half, another one of spin 1. So what is the dimension of the combined Hilbert space? I feel that you'll be able to do this. How many multiplets do you expect? And what are the total spin quantum number of the combined system? So if you go and look at the Clebsch-Gordon series or coefficients, or addition of angular momentum, you will find all the relevant information there. Okay, for the multiplet with the biggest spin, write down the highest weight state, which is easy to do. Then using the lowering operator, find all the other states, okay? So that's also easy to do. Now continue this for the other multiplets, okay? So do you guys see what I'm trying to do, what you have to do here?
Yeah, I think I got the gist of what to do. Like, I'll have to go through the
You got
lecture.
it? What about other people?
I'm a bit confused about the question.
Yeah, let me know.
I mean, for the multiplet, writing down the highest weight state and those, like, what basically I have to do.
Well, you know what? It's going to be J equals to Bj plus 1 J2, right? I've given you what J1 is, J2 is. So you start with the highest weight state of this guy and use J minus. And then, we did this in class, as you do J minus 1, you also have the right-hand side, and then, these coefficients are determined. And
So
will
I start with like Jj is like the tensor product of J1 and like J2. Like, do I have to like provide any proof for that, or I just write?
But you have to provide proof. You have to use formula which was done in class. I mean, if I give you two spins, what are the possible values of the total angular momentum? It starts with J1 plus J2, and then you go one by one down to, if J1 is greater than J2, go down to J1 plus J2. These are the total angular momentum of each multiplet, right? And first you start with this multiplet, find all the states, and then you start with this multiplet. But how do you find the highest weight state of this guy? Well, it should be made out of the same states of this thing, but a different linear combination. Since you have found this out, you can find out what this is, right? I mean, this was done in class, okay? Nahi, do you follow what I'm saying?
Yes, sir.
Yeah, if you go and look at the addition of angular momentum, you will find the algorithm there. The algorithm is that you first find out the whole multiplet for this thing. If you have the highest weight state, so you have to express in terms of, J1, M1, and J2, M2. You have to express, these guys, J, whatever the, J of M, whatever the total thing is, in terms of these guys. That's what you have to do. And the way you do it is that you first look at the highest weight state here, which is very easy to write out. And then you apply the lowering operator and you find the first multiplet. And then you go to the second multiplet and the highest weight state of this guy, you guess it by looking here, and you find that it must be made out of the same basis states as this one. But you have to take a different linear combination. If there was a plus sign here, you take minus sign here. And once you've found this, you again apply your lowering operator, and you do this until you find J1 minus J2. And in this case, how many multiplets do you think you will get? What is J1 plus J2? It's 3/2, right? In this case, do you agree?
Yes.
Hello? Okay. So what is J1 minus J2 in this case? It's half. So
Half.
can you tell me how many multiplets you're going to get? Just two, because just by when you go once down, you are coming from here to here, so you're not going to be able to go further down. So there's only two multiplets, right? And of course, this thing, your particle was 1. It was a tensor product between 1 and half. So the dimension of this guy is 3. The dimension of this guy is 2. So you're going to get 6 dimensions, right? And over here, these should add up to 6 dimensions as well. Okay, so do you guys see that idea? I think, go back and try this. This is not very difficult. I mean, but you have to understand the lecture on addition of angular momentum. Otherwise, you won't. And I gave that lecture twice. I gave that once, and then, we ran out of time. And then the next lecture, I essentially repeated the whole thing again. Okay, so if you are not able to, if you don't try to apply those ideas to problems, you're not learning stuff, right? So, which might be my problem, but you have to try, okay? Okay, let's move to problem 4. So this is just algebra, okay? Did someone do it?
Yes, I'm finished with it.
Okay. This is just algebra. There's nothing. Okay, number 5 is a bit physical. And you don't really need a lot of details here. You can use hand-waving arguments mostly. I think the first part you have to do some stuff, right? Yeah, you have to figure out the 3 by 3 matrix X, Sx, and then, was that difficult?
No, 1 was easy.
Anyone else? Did you find 1 of problem 5 easy, or should I tell you how it's done?
I haven't tried it yet, so I'm not sure.
Well, essentially, the two-dimensional version of it was done in class, right? You basically find out what is the SZ basis? It's 1, 0, and -1, right? And then you find out, what this is, right? But this is the the SZ basis, and that gives you a 3 by 3 matrix. Okay, and how do you do this? Without actually writing this down explicitly, how do you do this? You express it in terms of your raising and lowering operator. And then you know that if S plus X on, say, +1, it's 0. If S plus X on 0, you get 1, and you have to figure out what this coefficient is by using those marvelous formulae. So yeah, that's it. But then the second one is more physical. Okay, so it's saying that you have a Stern-Gerlach experiment, and the first filter, so you have a Stern-Gerlach experiment, and you get some beam, but it's a spin 1. So then this is your magnet, and you get 3 beams. So what you do is that you block 2. So this beam has Sz is H, and then it goes through another filter which just filters out the Sx component, and then finally it goes through another filter which has only the minus H component. So what fraction of the original particle goes through the whole setup? Has anyone done this?
Oh, no, sir. After you said it can be done physically, I'll try it that way. I mean, প্রথমে mathematically try করতে some three
Yeah, try to think of
dimensionalization.
it physically, right? You just think of, okay, the beam that goes through, which is the S, yeah, S, H operator. What should it consist of? I mean, this is essentially 1, 1, right? That beam is 1, 1. Well, we don't have to even write this first one. We just have to write 1. What should it consist of? What do you think? Should
It
nature?
consists of all the possible
It should
x
yeah.
lengths.
So if you right, so this is on Z basis, right?
Mhm.
So if you you just have to express it in the X basis. Okay, but I bet that whatever coefficients you get C1 of X1, C2, say X0, and C3 of X minus 1, so my intuition tells me that these would have the same magnitude. Do you think, can you confirm that, someone?
Intuitively, but
Yeah, but your intuition may not always be correct, right?
yes. So since we are, putting it in the Z eigenstates, the X eigenstates becomes arbitrary. So,
It becomes what?
the X eigenstate becomes arbitrary since we are in one particular Z eigenstate.
Yeah, exactly. But we don't really care about the exact coefficient. What we care about is what are the probabilities that they give rise to, right? So is there an easy way of doing this? Let's see. So right, so let's do this, okay? So this is Z1, right? So then what we should do is that we should express this in terms of the X spaces. So we should have XM, XM, we just insert and so basically we have to figure this out, right? So this is basically what it is. So how would you do this? Yeah, I'm just trying, we can always do a longer linear algebraic route. We can take a longer linear algebraic route, but I'm just trying to see if there's an easier way of doing it, right? Any ideas? And we can always say, okay, we can always say, let's just first figure out what this is. Maybe that's what we need to do. Yeah, probably that's what we need to do, right? So this is, we know what this is in the Z basis. So we just basically solve this equation. It's not very hard. I mean, it's just a few equations, right? This is a 3x3 matrix, and there's no like general, there is no general, the angles are all, pi by 2. So it's not like a big deal. You see what I mean? Right. So, and what we actually need to know is, what are the values, relative values of these guys, right? For M1, 0, and -1. Okay, so I would recommend that you do this explicitly, because the first time you do something like this, your intuition might be wrong, because there are 3 polarizations of these. I would recommend that you do it explicitly. Okay.
Okay, sir.
Okay, sir.
Okay, let me just move on to the last one. So the last one is the easiest one. So did anyone figure it out? Problem 6.
Oh, I was just confused about the age, but I think I can do it now.
Well, I mean we have been using both units where h bar is 1 and sometimes h bar is not 1. And here h bar is not 1.
Yes.
That's it, right? So all you need to think is that nature is symmetric. Although we prefer to work in the Z basis, nature doesn't care what you call Z and what you call X. Okay? So if you
sir, I mean, like, do I have to evaluate the matrix elements like মানে প্রথমটা কি SZ এর বেসিস এন্ড দ্বিতীয়টা কি লাইক SX এর বেসিসে নাকি দুটোই সেম বেসিসে ইভালুয়েট করব?
Well, matrix elements are numbers, right?
Yes.
Yeah. I mean, why don't you try? I mean, you're going to find that interesting. I mean, I can see the answer.
Sir, I was asking, like, should I find the matrix elements in the basis of in a particular one, নাকি which is S প্রথমটা SZ আর দ্বিতীয়টা SX like
It doesn't matter.
oh
It doesn't matter. Okay. You can always express one in the other, right? So suppose you do the first one in the Z basis. What are going to be the, so these are what? 3x3 matrices, right?
yes sir.
So if you suppose you do the first one in the Z basis, what will be the answer? Tell me.
It's just the eigenvalues along the diagonals.
So what are the eigenvalues of Fz?
1 0 and -1.
For h, minus h, and plus h.
Oh yes.
So what will be the expectation value of the first thing in the Z basis? Sz will be either h, or it'll be minus h, or 0.
Yes sir.
So what would be the product of these 3 factors then? if we apply this operator on an eigenbasis of Z, what is going to be the possible values of this operator? If you apply it on an eigenstate, doesn't matter, you pick one. Suppose you pick the eigenstate where the eigenvalue is plus h bar. What is the value of this operator then? Okay, think about it and you'll have the answer, okay? It's very easy. And the second one is very easy. You just have to square it. Right? You just square it, and when you take the Hermitian conjugate J minus, you get J plus, and you take the sandwich of this, and then you use the above formula, which is J squared equals to JZ squared plus J minus minus H bar. Should I explain the second one? So we have J minus acting on Jm, and that gives you C minus Jm minus 1. So if I take its Hermitian conjugate, I get Jm J plus equal to C minus star J M minus 1. So if I take the inner product of these two guys, the left-hand side is Jm J plus J minus, sorry, this J minus, and then this is Jm, and the right-hand side is C minus squared times 1. And this we can simplify using this other formula, and then you have the value of C minus 1. So that's an easy way of doing it, okay? So, okay, I think the one before is, so problem 6 is very easy, You just have to use your brain a little bit. Okay, any more questions?
No, sir. I think I'll be able to solve some of them. Well, most of them, I
You'll
think.
be able to solve all of them.
Within the given time, I might be able to solve 75%.
You can take as I'm saying, there is essentially no deadline. The deadline is really just for me to be able to be on a schedule so that I can give out enough assignments. So for example, today was the quote unquote deadline. And what I'm going to do now is that after the next lecture, after I'm done with hydrogen atom, which might take 1 or 2 lectures, I will give you assignment 3. And after that, I will do path integrals. After path integrals, I'll give you assignment 4. You can just try to keep doing it. I will start grading the stuff that has been submitted. But, as long as you finish it, all the assignments, 7 days before the final exam, that's fine too. But, you shouldn't try to do that, because it'll be detrimental for yourself, right? If you you will not be able to finish it, and you will just you will just lose marks. Okay, if you care about marks, which you should if you want to do higher studies and stuff. And also, it's good for your ego, and you learn stuff, right? So it should be in the other order. Yeah, you learn stuff, you need higher studies, and then your ego. Actually, ego is better than higher studies, because if you have self-confidence, then you can do a lot. Okay, so any more questions?
No, sir.
Did you figure out the answer to 6.1? Don't tell me. Don't tell anyone. If you just did, just say yes.
No, sir. I still
Okay.
haven't.
Okay. Just consider what would be the answer if you apply that operator on an eigenstate of Sz. And similarly, you can do the same for Sx. What will happen if you apply the second operator on an eigenstate of Sx? Okay. All right, so any more questions? So if not, let's meet again. Day after tomorrow? I think. Yeah, that's Wednesday. I'm sorry again for postponing class yesterday. So I don't think we have like 8 minutes. I don't think it'll be worth our while to try to do any physics in the rest. Okay. And thank you for participation. Thanks Sujat for pointing out my mistakes. Okay, everyone was here. Amazing. Awesome. Thank you.
Thank you, sir.
Thank you, sir.
Okay, thank you, sir. Goodbye.
Okay. Okay, good.